In this video, we will continue to explore what functions are and use tables and graphs to represent functions as we look at functions involving equations with two separate variables. The directions for numbers 3 and 4 ask us to graph each relation and use the vertical line test to determine whether or not it is a function. What makes these problems different is that they involve an equation relating the input or x value with the output or y value. In math, almost all meaningful relations will be shown in the form of an equation or an inequality relating the input and the output. We need to know that the solution to an equation with two different variables is any ordered pair that makes the equation true. So I've listed a number of different ordered pairs, and they've all been graphed on our coordinate plane. I need to know that most of these will graph in the form of a straight line, which makes them a linear function in this case. They don't all graph in a straight line, but most of them will for now. So where do these ordered pairs come from? I need to understand how to find them because they won't always be provided. I can always choose any x value and substitute it into the equation to solve for the y value to find the ordered pair. For example, if we start with the original equation, which you always want to do, y is equal to x plus 3, I can choose an x value. Over here you'll see I have a t-chart with x and y values that help me to keep this organized. The first x value I happened to choose was 0, so now I substitute into the equation for x equals 0. So in place of x I now have a 0, and y will now equal 0 plus 3. When I solve the equation, 0 plus 3 is 3, which tells me when the input or x value is 0, the output or y value is 3. So in our t-chart, I have an x value of 0 and a y value of 3. Together they make the ordered pair 0, 3. I can do that again. For example, when I choose the x value 1, I start with the equation y equals x plus 3. Substitute 1 for x this time, so y is now equal to 1 plus 3. And that means y is equal to 4. So again, when x is 1, y is 4, and that's where our second ordered pair comes from. Something else you should know about equations with two variables is there are usually an infinite number of solutions, because again, a solution is any ordered pair that makes the equation true. That's why our graph is always in the form of a line with arrows on both ends. That shows that that relationship continues forever in both directions. So our line must go completely across the graph from one end to the other and have arrows on the ends. In order to draw an accurate line, it's very important to be able to recognize the pattern that's allowing us to move from one dot to the next. For example, when I look at the dots that are graphed, I notice that the pattern is up 1, right 1, up 1, right 1. So I need to continue that pattern of going up 1 and right 1 until I'm at the farthest end of my graph. And I want to mark that point to use in drawing the line, because the further apart my dots are that I use, the more accurate my line's going to be. And that's very important because each point on the line represents a solution. I also need to be able to reverse that pattern. So I notice I can go down 1, left 1, down 1, left 1, and I want to extend that pattern to the other end of my graph, and going down 1, left 1 until I get to the furthest edge of the graph and I plot a point. Now I can use these 2 points to draw a very accurate line the whole way across my graph. Before we continue, it's important to clarify a few points. First of all, while I only showed you where the first two ordered pairs come from, the same process is used to find the other ones. So I chose an x value, substituted it into the equation, and solved the equation to find the corresponding y value or output. Now I could do this an infinite number of times by choosing different x values, but it's important to choose at least 3. That way you'll know if your line is graphing in a straight line, and it helps you to find out if you've made a mistake. I can always draw a straight line between 2 points, but if I get 3 that don't match up, and they should, It helps me to know that I have a mistake somewhere and I need to check it and fix it. Secondly, we need to talk about what we mean by every point on the line represents a solution to the equation. So for example, let's say that I plot a point on the line located right here. That particular point is located at the ordered pair -4, -1. This tells me that if I substitute that ordered pair into the original equation, y equals x plus 3, it should make the equation true. So my y value is -1 equals my x value is -4 plus 3, and -1 is equal to -4 plus 3 is -1. That makes my equation true. Now I can determine whether or not this particular relation is a function. Again, our vertical line test tells us if there's anywhere I can draw a vertical line that will pass through more than one point of the solution, it can't be a function because that would indicate that the input or x value is matched with more than one y value. As I look at this graph, there's nowhere I could draw a vertical line that would pass through more than one point of the solution. So is this a relation a function? The answer is yes. And it's a function because it passes the vertical line test because there's no input or x value paired with more than one y value or output. Number 4 is a very interesting example of an equation in two variables where the relation is not a function. You may notice from the graph before we start it's nonlinear. It does not graph in a straight line. So again, I have listed a set of ordered pairs that can be graphed, and we arrive at those ordered pairs in a very similar fashion. Well, we will almost always choose an x value and solve for y. In this particular case, we don't have the mathematical background to do that yet. So here we're going to choose a y value or output, square it, and then find the corresponding x value or input. So for example, let's say that I choose a y value of -3. I start with my original equation, y squared equals x. If I choose the y value -3, and remember the base must be inside parentheses to include a negative sign, I get -3 squared equals x. -3 squared means the base number -3 multiplied by itself 2 times, and -3 times -3 gives me a +9. So when y is equal to -3, x is equal to 9. That's my first ordered pair. I can choose, again, any y value in this case, so I'm going to choose next -2. I start with my original equation, y squared equals x, substitute -2, and -2 squared is now equal to x. -2 times -2 is a +4. So when y is -2, x is 4. Unlike linear equations, when I have a nonlinear equation, something that's not going to graph in a straight line, I need to choose as many input or output values as necessary until I'm sure I know where the line is going to be going. Once I've found enough ordered pairs like this and plotted them, for example, if x is +9 and y is -3, +9 on the x-axis is here, -3 on the y-axis is here, so that's 9, -3, and I've plotted all of those points. I now have a good idea of where the line's going to be going. I don't want to try to connect the points in a nonlinear relation using straight lines, because all of this curves. Remember, again, every point on that line represents a solution, a set of ordered pairs that will make this particular equation true. Now I can use the vertical line test to determine whether or not the relation is a function. Notice a vertical line can be drawn through more than one point of the relation. So this fails the vertical line test because you can find an input that is paired with more than one output. For example, the input of x equals 6 is paired with 2 separate y values or outputs. So, is the relation a function? The answer is no. Now let's practice finding solutions to an equation with two different variables when everything isn't already set up for us. So I notice the equation y is equal to 5x. I can choose any input or x value and plug it into the equation and solve it for the corresponding output or y value. But this is a good time to talk about the fact that I can change intervals on the graph if I need to. While I actually wouldn't need to do this for this particular equation, there will be equations we get to where it's impossible to graph on the space provided if each line represents 1. Anytime there are no numbers on the coordinate plane, we can assume that each line represents 1. In this case, by labeling 10 for two lines, I know that each line is worth 5. So this would be 5, 10, 15, 20, or -5, -10, -15, -20. I chose to label every other line rather than every line so that it didn't get too busy and to make it a little easier to read. Because the ordered pairs aren't already provided for me, I want to create a t-chart for my x and y values. Now, while I can choose any input or x value, it's important to choose values that when they're plugged into the equation and solved for the output, that will allow me to plot them on the graph. So for example, if I chose an x value of 1000 and I substituted it into the equation, y equals 5x, where x is equal to 1000, I would end up with y equals 5 times 1000, and 5 times 1000 is 5000. Clearly, I would have a very difficult time plotting that on this graph. So instead of choosing any random x value, I want to choose values that will be easy to graph. Because I chose to make intervals of 5 on this graph, it makes sense to have x values that are in intervals of 5. If I don't, I'll have to plot them in between lines. So let's say I start with x equals 0, which is usually a pretty easy choice. I start with my equation y equals 5x. I substitute 0 for x, so y is equal to now 5 times 0. And y is equal to 5 times 0 is 0. So when x is 0, y is also 0, which gives me my first ordered pair of 0, 0. Again, while I could choose any x value or input, I want to pick something that's easy to use here with intervals of 5, so I may choose x is equal to positive 5. Going back to my original equation, y equals 5x. Now substituting 5 for x, y is equal to 5 times 5. And y is then equal to 5 times 5 is 25. So when x is a positive 5, y is positive 25. Now I'm going to try a negative 5 for x so that I don't get a very large number here. And my original equation says y is equal to 5x. Substitute negative 5 for x, y is now equal to 5 times negative 5. And y is then equal to negative 25. So when x is negative 5, y is equal to negative 25. So my next two ordered pairs will be 5, 25, and negative 5, negative 25. Again, I want to choose at least 3 to see if it's going to be a linear equation. Now I'm going to plot those points on the number line, keeping in mind the fact that I have intervals of 5. So 0, 0 is located right here at the origin of the graph. Positive 5 on the x-axis and positive 25 on the y-axis is located right about here. And negative 5 on the x-axis, negative 25 on the y-axis would be located right there. Next, I want to look for that pattern between the dots to see if I can extend it further toward the edges of the graph. So if I start at the bottom left-hand dot, I notice I can go up 1, 2, 3, 4, 5 blocks and write 1. 1, 2, 3, 4, 5, write 1. But now when I try to go up 1, 2, 3, 4, 5 blocks up would put me off the graph. So that's as far as I can extend that. Again, the pattern could be reversed. I could go left 1 and down 5, left 1, down 5, but when I try to go left 1 and down 5, 1, 2, 3, 4, 5, again that would take me off the graph. So instead, I want to line up my ruler with the 2 points that are furthest apart from each other, And I want to draw my line again the whole way across the graph, making sure to include arrows on both ends, showing that that relationship continues forever in both directions. Now I'm finally ready to use the vertical line test to determine whether or not this particular relation is a function. When I look at my graph, again, there is nowhere that I could draw a vertical line where it would pass through more than one point of the solution. So this particular relation does pass the vertical line test and is a function.